All right, so today we'll be talking about the Rainforest Connection Species Audio Detection competition that just closed about a month ago on Kaggle. This is a competition that I was working on for a bit with some of my coworkers from H2O. And so we also have this other event. I'll let you talk about this, Ted.
Yeah, so actually this is going to be kicking off a monthly series. So on the fourth Wednesday of the month, we're going to have UCSD professors from the Data Science Institute there come in and do talks. And so our first one's going to be next Wednesday. I actually managed to just get the announcement out just before we start. So you guys might not have seen it, but I got it like right before the top of the hour. So this is going to be an NLP talk. And so if you're interested in NLP, there's here that are phrase mining, entity recognition, and then ultimately using graph networks to be able to deal with any kind of text, not necessarily in a particular structured format. So I'm actually looking forward to it. I think it's going to be a pretty cool talk.
Thanks, Ted. And so a little bit about me. I'm a data scientist at H2O working on automatic machine learning, and I do various other sort of consulting-ish type things with them. And I just recently got Kaggle Grandmaster. I got that last week, so I'm pretty happy with that. I've been doing this for several years now, working on different competitions, learning from all of this stuff that I can. And then along in the process, I became the organizer of the San Diego Machine Learning Group, along with Ted. So getting into the problem, what we were trying to do is we were trying to detect 24 different species of frogs and birds from audio recordings. So we're given some files and we just have to say, okay, which birds and frogs are present in this recording. The thing that we're specifically outputting though is the ordering of the likely species. So we're saying, okay, it's most likely that this specific frog is in the recording. And then what actually matters is the order of them. We're not saying in binary terms, this is present, this isn't present. We're just trying to rank them and say like, which are the most likely to occur in this audio. In terms of the data, we had 57 gigabytes of 1 minute FLAC audio files. So really high resolution audio, very high sampling rate, takes a whole ton of space, 57 gigabytes for not very many clips. And the way the data was labeled, it was there's two different distinctions. There's strong labeling and there's weak labeling in audio. Strong labeling is saying at this specific chunk of time, there's cheering, and at this specific chunk of time, there's laughing or barking or gunshots, etc. But then there's the alternate weak labeling, which is just saying this whole audio clip has these 4 things that happened in it. And in this data set, we had strong labels, but I'll explain a little bit more about that later. Some of them were partially missing. It was not completely strong labels. And so we were given 2 different files, one of them for the true positives and one for the false positives. We'll talk about that a little bit more later, what exactly the false positives were. The true positives were just the labels of this specific time, this specific frequency has this certain bird present, basically. And so what you can see in the bottom left corner is they're saying, okay, in this specific audio file, there's the species 14 during this time range and this frequency range, this is where the actual bird sound occurred for that species. Talking a little bit about the labeling procedure. So I thought it was actually kind of interesting what they did here. One of the problems is you have all of this unlabeled audio. So they basically have a whole bunch of microphones out in the rainforest, and then they need some way to say which birds are present or not. And so one way you could do that is you take your experts that are masters in all of the bird and frog sounds, and have them listen to hours and hours of audio, but that's not very efficient use of their time. So instead, what they did is they used this approach using template matching, where they basically selected golden samples of the audio. So they said, this is the best example of this specific species making their call. And then they use template matching, which is basically you take that little snippet and then you just slide it across all of the audio and you say where their reasonable matches. And then they went and they found all of those matches for the certain species, and then they had the expert look at it or listen to it rather and confirm, is this actually a match or is this just a false positive? And so that's where the false positives came from. The template matching would propose a whole ton of different times where the species might have been present, and then they had the experts actually go in and say, this is actually the bird, this isn't the bird. If it was the bird, then it went into the true positive file. If it wasn't the bird, then it went into the false positive file. So I thought that was an interesting method, and it obviously scaled really well because they were able to get a whole ton of labels fairly quickly rather than having experts listen to hours and hours of just dead rainforest audio. But one of the problems is that the labels are still incomplete in some way. They're still missing some actual things where the audio might have been there, but it didn't get hit by the template matching, and then it never had a chance of getting labeled by the expert because they weren't actually listening to it. And then in our training data, I think there were also some other issues that made the labels slightly incomplete. So that's a little bit about the labeling procedure. This is what they sort of look like. So these are the actual templates that they used in order to look for the corresponding audio. And this all came from, there was a paper actually written on the data setup and original model that they used. Moving on to the metric, they used this LWLRAP. The basic explanation of it is that you care about the rankings of your predictions. So I have some examples here to kind of explain that a little bit more. So let's say that you have a certain species and then the other two are missing, and then your prediction for them is saying 0.5 this, 0.7 this, 0.1 this. You actually want this one to be higher than all of the others for it to count as a correct prediction. And the way that you're penalized for it is you're basically saying, this should have been the first one, but actually it was the second one. So you get half credit because you were only off by one, basically. And so you can change this value. If you change it to 0.6, you've increased the belief that it's that one species, but it doesn't actually change the ranking. It doesn't exceed this 0.7. So you still get a score of 0.5. But if you finally increase it more and you get it to 0.8, now it's the first rank prediction and it matches with the label, then you get a 1.0. And so that's roughly the gist of this metric. It's also weighted based off of the frequency of the species in the data set, but that's just another implementation detail. The important thing is to understand how this ranking metric works. Looking at the baseline solution, so pretty much everyone did some variation on this. If you look at the public kernels, and if you look at other audio competitions in the past, they all kind of follow a similar formula. So we start with the raw waveform from the FLAC file. We turn it into a spectrogram. So this up here is the waveform. It's just a 1D series. And it starts out really, really long because you have your sampling rate, which on this data was 48 kilohertz, and then you have 60 seconds worth of it. So it's actually a very, very long series. And then you convert it to a spectrogram, which is this process of turning the frequencies into bins and then plotting it on this 2D plot. So on the x-axis, we have time, and on the y-axis we have the actual hertz, and then the pixel intensities change based on the volume. So if you have a very high-pitched sound, you'll have some brighter pixels up here, or if you have low sound, then you'll have bright pixels down there. It just depends on exactly what your audio looks like. And then once you have the data in this format, then it's something like this. You can change some parameters and end up with different dimensions. But with ours, you would end up with 257 bins vertically of the audio frequency, and then you have this long for the whole series. And with data of this shape, then you can pass it into a convolutional neural network, and you can treat it just as an image if you size it up correctly, because this is kind of big. But ultimately, this pipeline is fairly common in audio. And so what people ended up doing is they took 5-second clips. So right now, this is the full 60 seconds of audio. If you just cut 5 seconds of that, then you have 257 by a smaller number at that point, and then you can actually pass that to CNN reasonably, and you can train the model on that. One of the other things was the strong labels that we had. You obviously wanted to focus in on the regions of the audio where the audio was actually labeled. And so what people figured out is you can just crop in on the regions where it was labeled, and then you'll train more efficiently, because you don't want to train on regions that are unlabeled. And then at inference time, at prediction time, you might have trained on these subset 5-second clips that you cropped around the data of interest. But then when you actually do inference, you want to do rolling predictions across the entire series. So if this is 1,000 or 11,249, then you take 5-second clips out of it and you just do multiple steps across it. And then you do some sort of aggregation across all of those predictions, because you want to be able to capture, okay, here's the first 5 seconds of audio, do a prediction on that, which birds are present, and then you can move it another 2.5 seconds forward, and then you have half overlapping window. I've got another diagram I'll show in a second that can explain that a little bit further. So in terms of validation, it was actually really difficult, because the way that the test set was set up, the one that we're actually being graded against, they had that fully labeled by experts. So the experts actually went in and they said, okay, here's the 6 species that are in this audio clip. And that made it much more complete than the training set, where we just had the template matched and then expert verified solution, because it was possible that in the training set, we were missing species entirely because they were just never labeled. There were regions of the audio that were unlabeled. And so there's kind of 2 different trade-offs that you need to go between. So during validation, you can validate by just cropping into those regions where we know that the data was labeled in a certain way, or you can validate against the entire thing. And the trade-off is you're either validating against only a very limited set and just assuming that in the rest of the region, you're not going to get something wrong. So for example, if you are validating and you're just cropping right along where you know the data was labeled, but then when you do your inference later and you're predicting on the entire region and you get a false positive somewhere over here, then that causes problems for your model, and it makes it so your validation doesn't line up with the test set necessarily. But then doing the alternate approach, which is taking repeated strided crops of it, you end up with the problem of you're making predictions on areas of the data that is unlabeled. So you could actually detect a bird over here, and the label says nothing's there because the data is just simply unlabeled. And so your model yields a false positive, but you actually want it to find that bird there because it's just a missing label. It's not necessarily that it wasn't there at all. And so a lot of people found difficulty in validation here, is kind of the overall takeaway. there wasn't a great way to make sure that your model was actually being successful without actually looking at the leaderboard and seeing how it did against the professional labels. Looking at our solution ended up being very similar to the baseline that I laid out. So you take the waveform, you convert it to the spectrogram, you pass it to a CNN model of some sort, and then you just do that sort of strided prediction and aggregate in some way. We ended up with a fairly big ensemble of several different models. So there's lots of different off-the-shelf CNNs. There's various different ResNets and InceptionNet and EfficientNet and all kinds of different stuff. And so we used several of those. We plugged in different backbones, and then we eventually settled on, let's just take many of these models averaged together in some way and use that as our predictions. That was one way to get good variety in our models, was to use different backbones, but another one was using different clip sizes. So like in the previous example, we were training on 10-second clips and then moving it ahead 5 seconds at a time, but you could also do 5-second clips and move it ahead 2.5 seconds at a time. And so having different granularity of training gave it a slightly different view of the input. And so multiple different viewpoints gave it good good performance in combination. And so I think the thing that gave us the biggest boost actually was finding out that the test set had a significantly different distribution than the training set. For whatever reason, the training set made it look like the birds happened in a certain proportion. So the species 3 in our training set was not particularly common, but on the leaderboard, species 3 was in almost every single recording, either because it happened in a different geographic region, or it was missed by the template matching during the original labeling process, and it was later caught by the actual expert labelers. And so what one of my teammates did is they actually probed the leaderboard by just plugging in what happens if we always say that this bird is present and none of the other ones are present. And then they just went down the line on all 24, and then they figured out, wow, based on the results that we see off the leaderboard, we can see that this specific bird is very, very common, and we don't actually see it that often in training. And so they figured out, if we increase our probability of the two birds, the species 3 and species 18, then we greatly increase our score, because our probabilities are just not quite calibrated for it to happen that often. And so we just basically applied some distribution shift and said, okay, it looks more like this on the test set. And that was able to give us a very significant boost. And so during this process, we only used the true positive labels because we didn't really have a great usage of the false positives. But when I talk about other solutions, you'll see that people found fairly good benefit out of them. So some of the stuff that I specifically explored was trying to mimic the template matching procedure. So what I thought would be interesting is essentially simplifying our model so that it's just trying to do the same task as the experts, which is saying, given a small snippet of audio, just to verify, is it this species or is it not this species? But in order to get to that point, I needed to develop something that matched the template matching that they were doing, which would basically use those golden samples of audio and then find specifically the region that looks sort of like the bird. And so I tried various different things in that regard. One of them was, we have all of these examples of the specific regions that the template match found. And so trying to recover back the original template that they used, I tried to just basically average across all of those different templates that we were given. And so averaging all of those out, I would end up with something like at the top right. where it says, okay, generally it seems like this bird makes some sort of like increasing sound at the beginning and then maybe has some little tweet at the end too. Um, and so I tried various different iterations of that, and I was never able to make the template matching necessarily match what they mention in the paper. In the paper, they have a whole ton of detail about the different techniques that they tried, and I just was not able to match it. And I don't know if that was because I didn't have their actual golden sample, or if I was computing the spectrograms differently, or there's all kinds of different stuff that could have happened there. But ultimately, I just wasn't able to correctly mimic that. One of the other things was frequency specific models. So in our data, we can see specifically the birds only occur in this frequencies and the frogs only occur in this frequency. And we're specifically told the range that they actually occur in. So you can build a model that is specific to that frequency. So you say, okay, there's 24 different species. I'm just going to make a model that operates in 10 kilohertz to 15 kilohertz just to specifically target this certain frog or bird, for example. And in theory, that should be a bit more focused because it knows it's only looking for this one thing and determining is it there or not. It simplifies it from the perspective that it doesn't have to look across the entire range of frequencies for 24 different species potentially. We also tried various different aggregations across time. So we have that 10-second clip and then we're scooting it forward a little bit. And then what we're doing is we're just taking the maximum across time, basically. So in any of these clips, if I had some belief that the bird was present, then I'm just going to set it to the max value that was across all of that time. But you can also try different things like taking the average or doing different things with ensembles where you take the max from any of the models or something like that. And so what I started doing was looking at the predictions over time. So what this plot down here shows is for all 24 species, predictions across time. And so you would think that the predictions, at least the pattern that I would expect, is all of the predictions basically baseline at 0, and then it hears something and it would spike up to 1. And for this region where it thought the bird was present, it would be up at a high value. But in actuality, what we see is they're all just kind of calibrated differently across the entire recording. So for whatever reason, the background noise or something else environmental is giving it enough signal that it's just kind of sorting and it's saying, okay, these are the ones that I think are present given the background noise or the random other stuff that is going on. So it's not necessarily targeted enough to say, okay, exactly at this time region, spike up because I heard the specific bird, which I thought was interesting. I'm not entirely sure why that happens. Other people ended up making models that I'll talk about a little bit that captured this a little bit better as the prediction over time. We also tried transformers and LSTMs and some other time series based models, but ultimately just didn't have anything that ended up being as successful as the CNNs. So looking at the #1 solution, lots of interesting insights came out of this one when I was reading through it. So they used an ensemble of CNNs. So they used similar model to what we used, but they also did a combination of weak labels and more granular on the time axes with hard labels. And so they did this interesting process where they did with what we did, where you end up with a spectrogram, but then instead of having the model directly output 11 or 24 different binary outputs, they actually had it output across time. And then they labeled the data based on the time ranges and the species. So if you look down here, what they're actually showing, or down here rather, is the label. They're showing that this whole region of data is unlabeled, basically. but then this region might have been an actual 0, and this region might have been an actual 1, for example. And so the model is outputting the predictions across time on the x-axis and species on this axis. So your goal is to try to get the model to output correctly across time here, basically. And then they used this masked loss that basically said, okay, these whole region is unlabeled. Only the specific parts where we're told the answer actually care about. And so I thought that was an interesting insight. And then the goal is to get the model out here to output this sort of time series prediction across the species to light up like this one does. They mentioned that they relied on the leaderboard for validation. I think that was kind of a common theme across all of the top solutions. There really wasn't a great way to locally validate because we just had incomplete data, basically. And on the final set, it was actually complete, so you could grade properly. They mentioned that they hand labeled some of the missing annotations. And so they actually went through, they listened to the audio and they said, okay, I recognize what this bird sounds like now. And they plugged in some spots where they noticed that they were missing the correct labels. And then they also applied this pseudo labeling technique, which is basically you take your model's predictions and then you apply that to more data, basically, and then you train on that again. And so this was useful in this scenario because we only have, for example, in this set, if this is all that we have labeled, then we're kind of wasting all of this audio if birds actually did occur there. And so you train on this region and then you make a prediction on this region. And then all of a sudden we have all of this new labeled training data. And that's kind of the idea behind pseudo labeling and what a lot of people found success in this competition. Looking a bit more at their solution, so they had that combination of the hard label model that was across time, and they also had a weak labeled model. And what this weak labeled model did is it's actually predicting on the full 60 seconds. So going back here, so they had their strong labeled model that is doing predictions at this granular level. And then they also built a second model that's at the weak level that just says, take this full 60 seconds of audio and just output a prediction for the whole thing, saying these are the 4 birds that are present, for example. And the way that they did that, because we were actually missing the labels for significant portions of the audio, is they used the pseudo labels from the previous region. So they built their first strongly labeled model, and they made that as strong as they possibly could. And then they made predictions across all of the data, hoping that it would be complete labels at that point. And then they trained the weak labeled model on top of it. And then they also added in their hand labels. And so the way they set this up is they said, okay, pseudo labels, those ones count as 0.5 because we're not completely certain about those. We think they're pretty good predictions from our previous hard labeled model, but we don't know if they're perfect. So we'll just give those a weight of 0.5. But our hand labels will give a weight of 1, and then the actual formal labels that we were given will also weight those as 1 because we know that those are accurate. And then they also introduced this concept of a noisy student model. And so basically, the idea behind this is they had 10 different strongly labeled models, and then they would teach the weak label model from a random sampling of that. So if you have 10 strongly labeled models, you take a certain 60-second clip of audio, you give it the predictions from one of the models, and you have the weakly labeled model try to predict that. And so in some ways, it's distilling the knowledge of all 10 different models into that one weak labeled model, potentially. And then similar to us, they figured out some post-processing, so they understood there's a difference in the distribution between our training set that we had labels for and the test set that we don't have labels for, but we can probe the distribution out of it. And so they figured out that they could alter the distribution in some way and get a much higher score from that. So the second place
Hey,
solution,
Ryan,
yeah, go ahead.
can I ask a question? So the actual submissions that the #1 team made, were they from this ensemble trained weak label, or did they still ensemble the actual predictions from the hard labeled models with the weak model?
They used both in conjunction.
Okay.
Yeah.
So they used those hard to train the weak, and then they took some collection of hard and weak and figured out a way to ensemble all of them together.
Yeah. Yeah.
All right. Thanks.
So that's what they're showing in this diagram they made over here. They actually had many different versions of all of these different models, and some of them are using inputs from the other ones. And so there's this whole complicated slew of things that's happening here. And then they're just blending them in a whole bunch of different ways and then doing some distribution shifts and then taking the average of them. So they're throwing the whole kitchen sink in there and just blending it all together.
Thanks.
Yep. So the second place solution actually turned out to be significantly simpler, in my opinion. They ended up using a similar masked loss where it basically said where we have the labels for the true positives and the false positives, we'll count those as ones and zeros, but anything outside of that region for different species that might not have been labeled, then we'll just leave it as nans. So it won't actually compute any loss there. It only computes for the certain species where it was labeled and the certain timeframes where it was labeled. They used a similar concept of the pseudo labels, and so they basically took their original model and then they applied it across time at tiny little 0.5 second segments, and then they just rolled that across the entire thing. And then in essence, they've kind of replaced their missing labels that they didn't have at the beginning. So they did that step multiple times. So you train an original model, and then you train a second model that is trained on the original labels plus the pseudo labels that were created from the previous model. And so you can just kind of iterate that loop multiple times and continue to improve your predictions potentially. And so they said that they would do that 4 to 10 times potentially until it seemed like the model was no longer improving in any way. One of the things that they pointed out was that they added another channel to the input to their model, which was basically just a gradient going from top to bottom. So one of the special features of a convolutional neural network is its translational invariance, which basically means that it's designed mostly for vision systems. So let's say you have a dog in the top left corner of a picture. It should be exactly the same as a dog in the bottom right corner of a picture. It's still a dog. But that's not actually what we want in this scenario, because the y-axis, the frequency, we actually care a lot about the variation because we know that a certain frog isn't going to have a super high-pitched sound, but in theory, our CNN doesn't really explicitly have that information of where it is. So in order to encode that in some way, they just made a gradient going from top to bottom, basically just iterating through the range from 0 to 1. And so giving it that extra information seemed to benefit it a bit because then it actually knew what frequency it was looking at when it was doing the convolutions across the image. Looking at the third place solution, they used a blend of 8 different models using a combination of the true positives, the false positives, and hand labels. So their post-processing ended up actually being significantly simpler. They just thresholded species 3 in some way They didn't really put too much more detail there. So for ours, we actually changed the weighting based off of what we saw the leaderboard just for species 3 and species 18, but I think some other people actually did a little bit of tuning on all of them. For these guys, they only use species 3 post-processing. And then they also mentioned that they did a big hand labeling effort. So they actually went into the audio. They listened to almost all of it. They said that they ended up getting efficient enough that they were doing 300 audio clips a day, just going through and marking off all of the missing labels, basically. And then on top of that, they found some external data. So they found additional recordings and they were able to label that as well and then train on that on top of it. They used a whole bunch of augmentations. So one of the things that's interesting about audio versus images is images, a typical technique is to do various different augmentation techniques where you're saying, okay, here's a picture of a dog. If we rotate it 3 degrees to the left, it's still the same picture of a dog, but it's now a slightly different view of it. And so we can train on it again and our model learns something a tiny bit different. In audio, you can't do a rotation of audio. You can't do a flipping. There's lots of operations that don't really make sense in the spectrogram domain. And so they had to come up with various different augmentations of their own, adding in Gaussian noise, adding in other audio clips with different backgrounds. So they looked at this free sound 50K set of audio and they plugged in random car horns and stuff like that, just to make it robust to other random things that are happening in the recording. And they seem to have good results out of that. Interestingly, this is the only top-end solution that didn't use pseudo labels, but I think that you can kind of write that away because they just actually hand labeled it. So they didn't have to use pseudo labels necessarily. At least that's my belief. Maybe they would have gotten use out of pseudo labels anyways. They just didn't quite have the right implementation of it. It's hard to say, but I think that we can kind of explain that by saying their hand label probably filled in the blanks that the pseudo label would have. So looking at other interesting solutions and tricks that I saw from people. So the number 11 solution actually used something similar to what I was describing, something that I had tried, which is frequency masked and time cropped inputs. So like I was talking about, if we know that the frog only occurs in 10 kilohertz to 15 kilohertz, then just train it on a model that only sees that range. And so he trained a model like that and it seemed to work for him. I never quite figured it out. One of the special pieces of that puzzle that people seem to have figured out is the masked loss, which was basically only training on the region that was actually labeled and only for the species that was actually labeled there. So that small detail might have been the difference between making that work and not working.
Hey, Ryan.
Yeah.
So for this approach, did this person have to have 24 different models with different frequency masks?
It's all actually one single model. So they have to do training and inference are very complicated, but it's a single model. So one single model. So in this example, it's 128 spectrogram bins. And so when they're training, they would say, okay, here's one sample of just this range and just this time. And then the model's job is just simply to say, is this species present or not? But you can use the same model with 24 outputs on all of the different ranges because the images are all exactly the same size. So it's 128 by 500, for example. And you can use the same model to then do a prediction on a different range. So if for example, there's another species that you're making a prediction on, then you just make a prediction on 0 to 50, for example, instead of whatever this range is. And so you can just apply the model to all of the different ranges. And so one of the things he mentioned is when you're doing inference, then he has to do inference 24 different times on all of the different crops, and then also slide it across all of the time.
Okay.
So it makes it significantly more complicated, but you can do it as a single model that's just taking lots of different cropped views of the same image.
That's cool. Okay, and then if you happen to have an example where there were two species that overlapped both in time and partly in frequency, then either you special case it or you just deal with the fact that maybe it's a little bit confusing because you've got a little bit of that frog in this example that you're labeling as bird only, right?
Mm-hmm. Well, that's the advantage of the masked loss, though, is you're not actually telling the model that any of the species aren't there. You're just telling it that the one is there. So you don't even compute the loss for the other ones. So you're not being penalized if your model actually says, okay, the frog is there and the bird is there, but you're only looking at the one label at a time. So you're only being rewarded or penalized for the stuff that is actually being focused on at the time.
Got it. Okay, that's really cool. Thanks.
Yeah. So one of the other tricks that I thought was pretty interesting that one of the other guys figured out was we corrected the distributions based off of leaderboard probing. So we just did a bunch of submissions and we said, okay, what is the actual distribution that we're predicting against? But what some other people figured out is there's a paper on this specific data set, and in that paper, it tells us how many times different birds were detected, how many of them were caught by true positives or false positives, et cetera. And so that's what this table is partially showing, is how frequent these different birds occurred. And so what people figured out is actually using this information, you can reweight your predictions to be in line with this sort of prior, because we know that overall the data set is going to look something like this. And then without doing any leaderboard probing, just using this meta information, you can reweight your predictions and it ends up doing better using that information. So that is all I have for today. I don't know if there's any questions at this point.
Cool presentation, Ryan. Yeah, so anybody wants to ask a question, feel free to just unmute your microphone. And if you either don't want to or are unable, if you post in the chat, I'm happy to read questions aloud too.
So I had a quick question. Oh, go ahead.
Yeah, I have actually two questions. So one is, I think a couple of weeks ago, I asked about the different data set, the Cornell audio data set, and you guys said that it's very unbalanced. Was this one slightly more balanced in the test set than Cornell one?
Yeah. This data set on the test set was fairly balanced, depending on how exactly you define that. I think that our issue with the Cornell data set that we were talking about is that there was a big gap between the training data and the test data. And on this data, there wasn't really as much of a gap. It was just that it was labeled incompletely on the training set. So it's slightly easier to actually do that transfer procedure.
Okay, thanks. And the second question is, I don't know if you've seen Google released a library called Leap on Friday. It's sort of their, I haven't read on it in details, but it's sort of their replacement for MEL for audio classification. Did you have a chance to look at it? Would it help here?
Potentially, I haven't heard of that. What did you say it was?
It's called Leap. It's in Google AI blog. I can post a link.
Yeah, cool. I'd be interested. I haven't heard of that though, so I can't necessarily say if it would be better here.
How exactly you did reweighting? have you done it after the predictions were done and computed, or you did it together with training?
We did it after the fact. So we basically just did our full inference process. We made all our predictions, and then we just sat there with a spreadsheet and literally said multiply this column by 1.1. And that was as simple as our post-processing actually was. So to change the distribution, it was just multiplying a column. We didn't do anything in the training procedure to try to manipulate it.
Why you didn't? Didn't you even try to put in class weights during prediction? It just seems, easier way to do that because you can cross-validate together with class weights.
We could have tried that. I'm not sure exactly how that would play with things, because the problem is we were just trying to move it to a target distribution that was entirely different. So I guess we could have, I think that we would have had to do some sampling in terms of the actual frequency that we saw the different birds. I'm not sure. I guess we could have weighted it in that way. That just wasn't something that we really thought about, I don't think.
If I can make a comment about that, class weights and oversampling help with your priors, but in my experience, even when you use those, you still may have calibration issues and still need to calibrate at the end. So ultimately, I think, what Ryan ended up doing, where they multiplied by something to calibrate it, they might have had a smaller number that they were multiplying things by, but they would potentially still have needed to do final calibration.
I see.
All right, so Ryan, we have one question in the chat from Rajinder. What difficulties did you find with overlapping bird/frog sounds using a CNN filter? So since audio overlapping is different than visual overlapping, so did you do anything to try to deal with if you had two species talking at the same time and their audio was, adding on top of each other?
We didn't really have too much problem with that. We did look at our error, and we did see that, like, in terms of the confusion matrix, there were two species that seemed to frequently get kind of mixed up. It didn't understand which was which often. I think it might have been species 3 and species 11, where basically it just thought most of the species 11s were actually species 3s. But for the most part, there wasn't a whole lot of audio overlapping in our data set, it didn't seem like. And it part of it is the frequencies are somewhat exclusive of each other. There are some species that operate in the same frequency ranges, but for the most part, they would operate in slightly different frequency ranges. So you could just tell that just looking at the audio. I don't know if I have a good example of it anywhere here. So, like, for example, in this one, if there's some bird making a sound up here and then some frog making a sound down here, there's no real overlap. It's fairly easy to see a separation between them. So there might be multiple sounds happening at the same time, but because they're split by frequency, they're fairly easy to separate.
So I'm thinking, sorry, 1 second, Steven, if I could. I'm thinking about this mass loss, and that might have helped when I was working on the Cornell bird call competition, because even our training set, you would have a clip that'd be 45 seconds that says, this is a really great example of what a robin sounds like. And the robin was actually making it sound from, like, seconds, let's say, 1 to 10, and from 40 to 50. And meanwhile, there could be a crow that's cawing occasionally in the background, and then there's also, like, other things that happen. And so when I was training with hard labels with no masking, and so I'm saying this is not a crow, this is a robin, and you know, it was problematic because a lot of these recordings had other species in them, even in the training set.
Yeah, I think it's an interesting technique. I think it worked well here because we also had the negative labels. So we had labels saying specifically, there's an audio here that sounds like this bird, but we know for a fact it isn't that bird. So we had very good signal to separate what is and isn't a specific species. I'm not sure if you had that on the previous competition necessarily.
No, I may have had to work to do negative examples, but still, you know, I ended up doing a very poor man's thing. Like I weighted the shorter clips higher because I figured it was less likely in a 5-second clip to have lots of other birds in the background. Although there were, I mean, when I just randomly listened to someone, there were ones where it's just constant sound in the background. But then this was really magnified by the fact, and not to beat a dead horse, but you know, because the test set recordings were such poor quality, like somebody's phone just walking around, it ended up that all of the true signals in the test set were really quiet, and they were as quiet as the background sounds that we were trying to ignore in the training set. So it really made it hard.
Yeah.
Sorry, Stephen, please, I know you've been waiting patiently.
Yep, no problem. My question is more generic, which is, do we know how this generalizes? So there was a lot of effort put into, you know, doing a good job of making it match the test result, right? That the competition provided. Is there any indication, or do we have any idea how well it kind of generalizes to the real world, as opposed to just the test set that was provided?
I think that that's a big problem. I was actually kind of complaining internally in our team and with my other friends that I feel like the results of the competition are not that interesting because we specifically did stuff that breaks the ranking of our actual models. So if what we really cared about was saying, we think these 4 birds are the most likely to have occurred, and then we made a post-processing step that completely changed that just for the sake of matching the test set, then all of a sudden our models and our pipelines claim that they're much more accurate than they actually are because we were just correcting the labels basically based on what we knew from the test set. One of the goals of this competition is actually to measure migratory patterns and see, is there a different distribution than there was last year, for example. And so if we're doing that shifting of distribution, we're encoding it in the model saying this is the distribution that we expect, and it's breaking what we're actually trying to measure. And so I agree with the point that you're bringing up, that it's been too customized basically to the test set. It's not truly generalizable.
Right. It just seemed like it was overfitting. Yeah, I agree. Okay, cool. Thank you.
Yeah, I have a generic question, but also when you're making your solution, I remember you said that you're ensembling various different CNN models. I was hoping to ask, like, what did you do to ensemble it?
For the most part, we just took the average. So if you have 24 different outputs from 8 different models, we just basically stood them side by side and then just took the average across all of them. We could have tried to do some special weighting or additional model on top of them, but we ended up finding that just taking the average across them was perfectly fine. And some other people actually mentioned that, some of the higher ranking people mentioned that they were doing various different attempts of ensembling, and they found that just taking their best single model was what was doing the best anyways. So we just took the average. There was nothing too fancy going on there.
Okay, cool, thanks.
So time for maybe at least one more question. Yuri has one in the chat. Yuri, do you want to read it or?
Yeah, I don't know if I wrote it well. So I just want to mention that, follow up on this example of two birds sounding the same but labeled as a negative example. Is it specific laws that help kind of use that information, or is just in general those labels help?
In general, those labels helped because the way the masked loss worked is basically if the bird was in the true positive file, then it would show up as a 1, but all of the other labels would just be nullified. They would have no impact. So if you only had the true positive file, eventually your model would converge to just have every single prediction pinged to a 1. So you also need to have the negative examples saying, okay, when this is marked as a false positive, mark that actually as a 0, and that will actually pull it in the opposite direction. And then you get the separation between the two classes because the way the mask loss works. If you didn't have those zeros, you would just have all 1s eventually with your predictions. I'm not sure if that fully covers the question.
And Ryan, just to be clear, in this competition, because they were trying to find good examples of the bird, the false positives, those zeros, were actually really good teaching examples because they were very similar to positives, but they were negatives, right? Like if you just had like white noise as your only negative examples, that might not really work very well, I would think.
Mm-hmm. Yeah, exactly. They were great negative examples because they were saying this kind of looks like the bird, but it's not. So I specifically want you to separate this out.
Thank you.
Yep.
Cool. Thanks, Ryan. I appreciate you sharing your experiences as well as going and helping summarize for us what other people did on this competition.
Yep. No problem.